This is the final unit, unit 6 on the dynamical systems primer, and this is about bifurcation theory. Bifurcation theory starts with the question: how does the dynamics of an ODE change as a parameter varies? And again, what we do is we look in the neighborhood of a fixed point. So we consider, what we look at then is the equation x dot is equal to f of x and mu, right? So again, x is in the phase space, u in Rn, but now we're having f also depend on a parameter mu, which is going to be a real scalar. In the problems that we're interested in, you could have more parameters, but that's usually what we think of, just varying one parameter. For instance, we could take the logistic equation and think of fixing S and let R vary. So R would be our mu here. Or going to the Lorentz equations. Lorentz system, we could imagine fix all but one parameter, which might be, say, rho, say this parameter here, rho, and let that vary, right? And see sort of how the dynamics changes near a particular fixed point, which is naturally the origin. But we may also be interested actually in the dynamics near other fixed points, the bifurcations near other fixed points. Okay, so let's look now at the basic bifurcations that can occur. Bifurcation suggests some kind of change and some sort of splitting into two, some sort of forking. So let's take n is equal to 1, right? That's the simplest situation. And the most basic bifurcation is called a saddle node bifurcation. So in this case, what happens is that, say, as the parameter, let's take 0 be the place where it changes. So if mu is less than 0, what happens is you have two fixed points like this. One of them is unstable and the other is stable, right? Or in fact attracting. And mu equals 0, what happens is that these two come together like this. So this sort of unstable bit is happening to the right here, and the stable bit is happening this. So it looks like this. And then what happens when mu is bigger than 0 is that fixed point actually disappears completely. That's called a saddle node bifurcation. What we do is put this information together in what's called a bifurcation diagram, where we draw, in this case, a two-dimensional picture where the parameter is one of the directions, say the horizontal axis, and the phase space variable is the other direction. So this says when mu is less than 0, there are going to be two, right? And then they come together when mu equals 0. So you can imagine then that the set of fixed points makes a sort of parabolic type shape like this, where if I take a mu less than 0, I have two, one here and one here, right? And on each vertical line, what I can do is place the phase space associated with that particular mu, right? So according to this picture, then this one is unstable and this lower one is attracting, right? And that is true all the way up to mu equals 0. We have an unstable fixed point and an attracting fixed point, and then here they come together and annihilate each other, and on mu is equal to 0 we have this picture. If if I put in here the mu positive dynamics, a vertical line there, then that is what happens in that case. So then now the next one is also in n is equal to 1, and that's what's called a transcritical bifurcation. Transcritical bifurcation. So in this case, what happens is mu is less than 0, you have 2 again, like this, and say this one is attracting and this one is unstable. When mu is equal to 0, they come together. Right? They come together and do this. So far it looks very like the saddle node bifurcation, but what happens now when mu is bigger than 0, instead of them killing each other, they kind of pass through each other and they exchange stability. So this one now becomes the right hand one. Now, well, you'll see why I call it exchange of stability in a second. Sorry, but that's a little misleading from this picture, isn't it? Okay, but this right hand one is unstable and the left hand one is attracting. That sort of looks the same as before, but if you think of this point here as being 0, then you see why it's called transcritical and why we say exchange of stability. So let's draw it like this. The way the fixed points look is this is a curve of fixed points at 0, and then this is a curve of fixed points that passes through 0. Over here, what happens is you have the 0 solution unstable and the other one attracting. When you come to this 0 here, they've sort of come together and it's neither stable nor unstable, but when you go to the right here, it's now the 0 solution that has become attracting and the other solution has become unstable. That's called a transcritical bifurcation, and it's sort of not hard to see that this happens in the logistic equation exactly like this. Okay, the third one is also happens in one dimension, and it's called the pitchfork bifurcation. Okay, and it works, the pitchfork bifurcation works as follows. When mu is less than 0, you actually have an attracting base fixed point here and just 1. But then what happens when mu is bigger than 0? When mu is bigger than 0, it splits into 3, like this. And the middle one here has become unstable, and the outer 2 are both attracting. This picture actually holds for mu less than or equal to 0, at least in terms of the basic dynamics. So if I look at the bifurcation diagram for this is mu and this is x. I've got a curve of fixed points, always at basically a sort of base state, which we assume to be at 0. And then I have bifurcating out of that a curve of fixed points here. Right? To the left here, things are attracting. That's also true when I go through 0. When I go to the right, though, it's the 0 solution has become unstable and the bifurcated solutions have become attracting. Okay, so this is called a pitchfork bifurcation. Again, a one-dimensional bifurcation. Okay, what happens in 2 dimensions? Well, the basic bifurcation in 2 dimensions, where n is equal to 2, is a Hopf bifurcation. Right? And the Hopf bifurcation is kind of similar to the pitchfork bifurcation, but instead of bifurcating 2 attracting fixed points out of the base fixed point here, what bifurcates is an attracting periodic orbit. Right? So the picture right now, this is now in 2 dimensions. When mu is less than 0, is going to be that we have an attracting fixed point, say at 0, right? This is 2D, so this is x1, x2. When mu is equal to 0, that still holds, like in the pitchfork bifurcation. So actually, I won't draw that. Let me just say that that holds when mu is less than or equal to 0. And when mu is bigger than 0, what's happened is that as bifurcated out of this is a periodic orbit. The 0 solution has become unstable, and these orbits inside here are attracted to the periodic orbit, and the periodic orbit is attracting from the outside also. Okay, now I can draw a bifurcation diagram for this, and it's sort of a little bit difficult to draw, but I will attempt it. This is mu. Again, the transverse space, which is the phase space, is x1, x2 is now two-dimensional. I have a curve of fixed points here at 0, right? And if I look to the left of 0, my picture is of an attracting fixed point, sort of spiraling in like this, right? Right. And now as I go through 0, this somehow changes, and in fact what happens is that over here, if I look at the picture, I actually have a periodic orbit going around this, and I have this spiraling out towards the periodic orbit. We can draw the bifurcation diagram for the Hopf bifurcation. But it gets a little bit harder if we draw the full picture, right? So as I said, we have these fixed points here. Now let's see what bifurcates out of there. Bifurcates out of there is this sort of paraboloid of periodic orbits like this, right? So that each mu value is a periodic orbit, right? And inside still are these fixed points at 0, which have now become unstable, and the periodic orbits have are the attracting things. I want to make a few comments here. The first comment is that the bifurcations that we've described in the pitchfork and Hopf go in a certain direction. So the ones we described, pitchfork and Hopf, given here, described above, are supercritical, or what are called supercritical. That is to say that above the critical value, or the bifurcation point, is when the bifurcated solutions appear. You can also have subcritical pitchforks and Hopf bifurcations. If I draw it in the case of the pitchfork, what happens is it goes off to the left, right, and to the right. What happens, right, is that this is attracting to the left, right, and this is unstable. The non-trivial solution is unstable, and to the right the trivial solution is unstable, right? So in some sense you can think actually then in sort of unstable solutions of bifurcating from the fixed point. And you can have a similar situation for the Hopf bifurcation. The conditions for the pitchfork bifurcation, being sub or supercritical, are not hard. For the Hopf bifurcation, they turn out to be particularly difficult to verify anyway. Okay, a second comment is that all of these bifurcations can happen in higher dimensions as well. Can occur in higher dimensions, and what you want to think of here is that they happen on the center manifold. So this ties in with the last unit. Can happen in higher dimensions on a center manifold. Okay, so in the next slide I'll explain how you see that. Just to see how these might occur on the center manifold, the idea is you add a state variable or a phase space variable for the parameter. Add a phase space variable for the parameter, right? So in other words, well, what's the parameter going to do? It's not going to change, right? So your dynamical system now becomes x dot is equal f of x and mu dot is equal to 0, right? That just says it's parameter because it's not changing. So now my phase space is u cross r, right? Where r is for the parameter value, right? So now imagine that right, x equals 0 is a fixed point, for all mu, say, near 0. Okay, so that's a fixed point for mu near 0. So in other words, you've got f of 0 mu is equal to 0. And now as mu varies, 0 stays to be a fixed point. But let's say at mu is equal to 0, we have a possible bifurcation, right? So there's a possible bifurcation at mu equals 0. So how is that registered? Well, that's going to be registered basically by a degeneracy in the linearization. Because if the linearization, if say d sub x of f at 0 mu is non-zero, or is non-degenerate, in other words, has no eigenvalues on the imaginary axis, then you have a full complement of stable and unstable manifolds that fill out the phase space, and there's nothing odd happening. So this possible bifurcation will happen at mu is equal to 0 if, right, d sub x f of 0, 0 has a 0 eigenvalue. So in other words, there's going to be a center manifold. But not just a 0 eigenvalue, it could also have eigenvalues on the imaginary axis. And that's actually when a Hopf bifurcation occurs. So let's imagine what's happening in the complex plane here, right? So now this is going to be the complex plane, the spectral plane, not the phase space. I'm just looking at what's happening to the eigenvalues, right? This is the spectrum we're going to be looking at here of d sub x f of 0 mu. Okay, the linearization of f at the fixed point 0 as mu varies. So maybe it has some stable eigenvalues, some unstable eigenvalues. Note the problem is real, so if I ever draw any complex eigenvalues, they have to come in conjugate pairs. But now imagine that an eigenvalue goes through 0. And actually at mu is equal to 0 is when the eigenvalue is at 0. That's the bifurcation point. We have this picture that the eigenvalue is actually moving through 0. This is exactly what happens in either a pitchfork or a transcritical bifurcation, And what you would do then is you would look at, in the phase space, x mu is equal to 0, 0. This is now in our expanded phase space, u cross r. At this point here, we would get what? A 2D center manifold, because you have one coming from one 0 eigenvalue coming from the spectrum of this, and 1 0 eigenvalue coming from the mu dot is equal to 0, because you're in this sort of augmented phase space. Right? And what you would see is you get a pitchfork, you get one of these bifurcations, right, on the center manifold, on WC log, which is now 2D, and in fact the dynamics on that, the dynamics on WC loc is exactly what you see in the bifurcation diagram. So it's exactly the bifurcation diagram. So the same thing happens for the Hopf bifurcation, but for the Hopf bifurcation, the spectrum is looking like this. Maybe there's some stable, some unstable spectrum. What happens is that two eigenvalues, which are complex conjugate pairs, go through the imaginary axis, but not at 0. And at the bifurcation value, they are exactly on the axis. So here then at mu is equal to 0, and so at the fixed point in the extended phase space 0, 0, WC loc is going to be three-dimensional, right? It's going to be one dimension for each of these two complex conjugate eigenvalues, and one for the mu direction in the phase space, right? And again though, right? And again, the phase space is exactly the bifurcation diagram. Phase space dynamics is the bifurcation diagram. Is the bifurcation diagram. All right, so that completes the last unit, unit 6 of this dynamical systems primer. I hope you'll see each of these sort of phenomena in action in the various things that you will look at. And all right, thank you for listening.